Hello, everyone, and welcome to another wonderful day of quantum mechanics. So, last time we built up the idea that all particles moved as a wave. Now we need to build up a wave function, which is again our way of talking about a mathematical equation that essentially describes all of the behavior of our new wave particle. So, one of the things that we're going to start with is by starting by trimming down some of our functions. So we're not going to try and deal with a multidimensional system. We're just going to look at a system that travels in one dimension with time. So this means I've got a wave and it may essentially move to the right or the left, but I don't have to worry about how this amplitude is going to change in, say, the x or y direction, or y or z direction. This will help keep the system a little bit simpler. This type of wave function is called the one-dimensional time-dependent wave function. Now, here's one of the tricks to keep in mind about the wave function. The wave function is not real. The wave function is not an observable. It's not something that I can pin down as existing. What it really is a mathematical equation that perfectly describes the system and can be used to determine all of the properties of a particle. So one of the best analogies I've heard about this is the wave function is an oracle. It contains all information you will ever need to know about a particle, but the real question is going to be, what's the right question to ask it? You ask the wave function a question, it will tell you some very good information, whether it's where my particle exists, how likely is it to exist in a given region, what is the energy, what is the momentum. It knows all of this, but the function itself doesn't really exist. And this is actually a fairly tricky thing. But one of the easiest examples of a property that we can get out of the wave function is the probability of finding the particle at any given point. Well, you can essentially get the relative probability of finding the system at any given point by simply taking the square of the wave function. This square of the wave function says, okay, I have this certain probability of finding the system at any given point. So while the wave function might not exist, this probability density is actually a directly measurable property that we can use, and we can actually compare. That said, it often means if you're able to measure the probability density, you have a better guess at what the actual probability, what the actual wave function itself will look like. However, now we know that the wave function is really important, it's very useful, but how on earth can we determine it? Well, one of the most robust methods was proposed by Erwin Schrödinger in 1926. This is the very famous Schrödinger equation. So we're going to start with a one-dimensional time-independent Schrödinger. So this means that I'm going to ignore any sort of change of my wave function with respect to time. I'm going to assume that it is constant and not changing. This is a little incorrect, but it's a very good starting point, just like dealing with one dimension at a time. So what this equation essentially tells me is I can apply a set of functions to my wave function, and I'll spit back an energy. So what we have here is, first, we're going to apply what's often called h bar. But what h bar really is it's the Planck's constant divided by 2 pi. Turns out 2 pi keeps showing up all over the place, so don't be too surprised if you spot an h bar. It usually means that some sort of trigonometric function happened along the way. Then we also have the mass of the object, and then we're taking the second derivative of the wave function. Then this next term's also a little bit tricky. It includes the potential energy of the system. So this is actually going to highly vary upon the system we're studying. Whereas this is actually going to be fairly universal because it relates to the kinetic energy. The potential energy, well, very system dependent. But by applying these two equations to our wave function, what we spit back is the total energy of the system. Again, times the wave function. So what's really useful about this is it's going to give us information about two different things. First, it gives us a way to determine the energy of our system, which again, we're physical chemists. We love to know the energy of our system. But second of all, it also gives us a way to try and determine the wave function. Because here's the important thing about a wave function, is that the wave function I have here on the left-hand side needs to be spit back out on the right-hand side, even as I apply a set of functions to it. So one of the good ways to try and analyze the system is by, again, focusing on simple, and we'll work our way back towards complex. So we're going to assume we're dealing with what's called a free particle. So this is a particle more or less traveling through a vacuum. It's not interacting with anything. There's no reason it wants to be in one location more than another. So if I've got a free particle, this means that I've got no potential energy. No place is better than another. So that second term drops out, and what we're left with is this first term. So now I need to apply a set of constants, so I don't need to worry about those. But I need to apply a second derivative to a wave function and get my wave function right back. So I need a function that doesn't change after applying two derivatives. That's a little problematic, as most functions will change when you take a derivative of it. But there are three special functions that are well known for satisfying this requirement. And not too surprisingly, they're mostly trigonometric. So our three general equations are sine, cosine, and an exponential. So sine, its first derivative gives me cosine, and the second derivative gives me sine back. So if that works for sine, guess what? It should work for cosine as well. And then we have our last oddball equation of exponential, where again, first derivative of an exponential, as long as the power of x is 1, is just going to give me a different constant. So the constants will change in each of these cases, because as I take the derivative of sine, I'm going to pull this k out. Same thing with the exponential. So let's go ahead and analyze one of these systems. So let's go ahead and pull typical solution for a wave function for a free particle, cosine. Who doesn't love a cosine? So if I take the first derivative of cosine, what I get is negative k sine. So again, derivative of cosine is negative sine. And then using chain rule, I have to do the derivative of the inside. This just gives me out k. So I get negative k of sine kx. Then I can go ahead and apply my second derivative to sine kx, because negative k is just a constant, so it pulls out front. Then I take my second derivative and I get back k cosine kx. Now what we can do is then put this together for a second derivative. And what we'll find is the second derivative of cosine kx is going to be negative k squared cosine kx. So as I apply my second derivative, I get my cosine kx back, but I get it with a negative k2. So the negatives cancel out, and I'm left with k2 cosine kx. Now, here's where we can actually compare it to the Schrodinger equation. Because the Schrodinger equation says if I apply this whole equation to my wave function, I should get the energy times the wave function. Well, here's my wave function. This means that everything else is going to be my energy. So using this solution, we can show that my energy is going to equal h bar squared, k squared over 2m. Now here comes the fun bit. H bar squared is a constant. H bar is a constant. Mass is defined by my system, but what on earth is k? And this is actually the fun part, because k can really be anything. So what we can do is say, well, if I know the energy of my system, I know the total energy of my system, often because I say accelerated an electron through a potential field. Well, I can then use that to find my k. So we can go ahead and then solve for k, and we find that my constant is going to be equal to square root of 2m times the total energy over h bar squared. Now we can essentially start making use of this E factor, because I might not know E, but let's relate it to potential. So I can give the total energy, which in this case, we know all of my energy is kinetic. So kinetic energy is equal to momentum squared over twice the mass. This is a nice, useful equation to have in hand. And this essentially comes from E equals 1/2 md squared. Same equation, just different application. So this means that I can solve for, I can input this equation into my energy expression when looking at K. So this gives me K equals, well, twice the mass times momentum squared over twice the mass times Planck's h bar squared. Well, my two m's cancel out, and all I'm left with is the momentum squared over h bar squared, but this is all to the square root. So here's the really fun bit. My K is now momentum over h bar squared, which I can phrase as 2 pi over momentum h. Again, using the fact that h bar is just Planck's constant over 2 pi. But we have an equation for momentum over Planck's constant. This is our de Broglie wavelength. So what we can do, or it's 1 over our de Broglie wavelength, because remember, de Broglie wavelength is h over momentum. So this means that my K constant for my wave function is just going to be 2 pi over the de Broglie wavelength. So let's go ahead and insert this back into our big long equation to illustrate a very important point. So our wave function for a free particle is cosine 2 pi x over the de Broglie wavelength. So this should actually hopefully make sense. Because if x is 0, I start with a cosine of 0. I get a nice value of 1. Who doesn't love that? Well, as x goes to 1, I now have 2 pi over my wavelength. And now now having traveled 1 wavelength, I've essentially now reached my negative node. So I've gone from down, or from up to down. And then when I get to a value, when I go to a full value of 1, I've now returned full circle. So what we have is an equation that perfectly models what we'd expect from the de Broglie relationship. So according to de Broglie, I should have a wave that follows this same general behavior. So this is a really powerful way of looking at our system. So what we're finding is that cosine kx is actually a satisfactory solution to the wave function of a free particle. So one of the important things is, again, how we interpret this wave function. So we're often doing this through the Born interpretation, which is actually very similar to what I've expressed earlier. Because we can, using my wave function, determine the probability of finding a particle essentially in between x and dx. And this can simply be given by the wave function at position x squared times dx. Now, you'll notice that we have a little bit of an odd squaring here. We have some upright brackets around my wave function that I'm squaring. Well, that's because what this is actually called is the probability density, and it isn't a simple squaring. It's taking our wave function and multiplying it times its complex conjugate. You may have not encountered the word complex conjugate before. So what a complex conjugate is it's simply taking my wave function and taking all of the imaginary numbers and slapping a negative in front of it. We'll deal with that later. But for now, we're just going to treat this as our probability density as the squared wave function. So again, what this is really showing us is that the square of the wave function is going to be proportional to the probability of finding that particle at position x, as long as dx is essentially sufficiently small. So as this goes lower, what we really do find is that the probability density is going to give me the proportionality of the probability of finding the particle at any given position. We'll deal with turning that proportionality into an equality later, but that's in our future. However, this gives us another way of talking about our wave function. It's occasionally also referred to as the probability amplitude, and it is worth noting that this is essentially just the intensity of finding the particle at any given position. Because remember, it can be positive or negative, which is one of the reasons why we have to take the squared here. But again, the larger the value, whether it is positive or negative, the higher my probability density, the more likely I am to find a system in a given location. However, one of the things that's worth noting is while we've developed this in terms of Cartesian coordinates with the position of x, it's also possible to denote this in terms of spherical coordinates, where we find the probability of finding a particle away from a given point. So in this case, we switch x for the radius or distance from our center point. So again, don't be too surprised. We're going to make use of some spherical wave functions occasionally. However, this now gives us kind of a rough view of what our wave functions should look like. Though I want to essentially pull up a couple key points. That in order to have a wave function that satisfies the Schrodinger equation, any equation won't do. We have to put a couple limitations, and some of these will probably seem kind of sensical. So the first of which is that my wave function can't be infinite over a finite range. So as long as essentially x isn't infinity, neither should my wave function. So this means that things like a classic exponential that goes like this, not so good. I'm going to want something that keeps in a finite value. So something that cycles is great. We also find that our wave function can only have a single value for x. So this means that I can't have any equations that circle back on themselves like this. I can't have a point, I can't have an equation where it has two values for a single x. So it has to essentially be something that looks kind of pseudo-linear. Next, and this one's actually very important because as you may have noticed, derivatives and second derivatives are very important to our wave functions because they're embedded in this Hamiltonian, which means that our wave function has to be continuous. So I can't have any breaks or gaps in my wave function. Similarly, the first derivative also has to be continuous because, well, I'm taking a second derivative, and a continuous first derivative means that I always have real non-infinite values for my second derivative. So we're going to explore the use of our wave functions a little bit more next time. Until then, take care.